Acetone. Acetone is a molecule made of these pieces: 3 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom put together like this. A more streamlined way of depicting the molecule is with a skeletal structure. In a skeletal structure, the carbon atoms are replaced by the ends or the kinks in a straight line, and the hydrogen atoms coming off of those are implied. Acetone occurs in a few places in nature. It's released in the eruptions of volcanoes and the huge clouds above them. It's released in large quantities from plants during forest fires. And acetone has even been found on comets. In fact, here's an up-close image of a comet on which acetone was found. Humans use acetone in a number of ways. The biggest one is industrial usage as a solvent. Acetone is produced in the millions of tons each year for use as a solvent. And one of the things that it's used, one of the reactions it's used for as a solvent is making plastics. So plastics are like plexiglass, are not made from acetone, but in order to do the reaction to make plastics, you need a bath of acetone to put the molecules that are going to become the plastic in for them to react with each other. And so these inches thick windows in this aquarium are made from plexiglass that was made within a bath of acetone, although the acetone itself was not part of the plexiglass. Acetone is also used as nail polish remover, and you can use it to dissolve superglues before they've dried. So if you've put superglue in a place and it hasn't completely dried yet, and you realize you don't want it there, you can daub it with acetone, and that will dissolve the glue and remove it from where you've placed it. Acetone is also used as a paint thinner. So if you combine all of the pigments and other ingredients in a paint and it's too thick, you can add acetone to sort of water it down. And once you apply the paint, the acetone will evaporate off of the wall. Safety with acetone. You could summarize the safety considerations with for a molecule with these fire diamonds or safety squares. The blue square on the left represents hazards to your health. It's on a scale from 0 to 4, where 0 represents no health hazard and 4 represents a quick death on exposure. Acetone is a 1 on that scale. It can cause mild skin irritation and moderate to severe eye irritation, so when you're working with it, you want to make sure you're wearing gloves and goggles. And if you breathe it in at high concentrations, it may depress your central nervous system. So preferably you would want to use this in a well-ventilated area and preferably a fume hood. The red square represents flammability. It's also on a scale from 0 to 4, where 0 is a molecule that will not burn and 4 is a flammable gas at room temperature. Acetone is a 3 on the scale, which means it's extremely flammable. Acetone can ignite even at very low temperatures. If you have a room that is negative 4 degrees Fahrenheit or negative 20 degrees Celsius, acetone can still ignite in that room and form enough of a vapor to ignite in that room if there's an ignition source. So it's extremely important that you keep acetone away from sparks, flames, and excessive heat. The yellow diamond on the right represents a molecule's instability or reactivity. That's also on a scale from 0 to 4, where 0 means a molecule will not explode, and 4 means it will explode at room temperature if disturbed. Because acetone is a 0 on that scale, that means you can shake acetone up in a container and it will not explode at room temperature. The white blank diamond at the bottom means there are no special considerations you have to think about when dealing with acetone outside of the health, flammability, and instability considerations. Visualizing acetone. As we saw, the skeletal structure of acetone represents carbon and hydrogen atoms put together like this. But this is a 2-dimensional depiction of a 3-dimensional molecule. In this molecule, you can see that the carbons at the ends of acetone are both tetrahedral, and the one in the middle is trigonal planar. In addition, in this 3-dimensional picture, you see these colors representing charges. A 3-dimensional picture where colors are used to represent charges are called electrostatic potential maps. Notice that oxygen is very electronegative, that's this red ball here, So it pulls electron density to itself and becomes slightly negative, and that's represented by this larger red color. Whatever it's bonded to loses that electron density and becomes slightly positive, and that's represented by this blue color here. So this carbon bonded to the oxygen is slightly positive. The thin band of green here is representing a place where the molecule is neutral, where there isn't a slight negative or slight positive charge. But these bonds are not still and static. They're dynamic, dancing, moving things. Each of these bonds at room temperature can vibrate around 10 trillion times. To give you a sense of what that looks like, what the molecule looks like as the bonds vibrate and rotate, here's a simulation showing those vibrations. I've played the simulation with about 1 vibration per second so that you could see how the bonds can move. But at room temperature, you can have around 10 trillion vibrations in 1 second. So to get a better sense of how the real molecules are moving at room temperature, let's speed this up 20 times. Now let's speed it up 400 times. A real molecule in a solution of acetone would be moving 25 billion times faster than the vibrations we see here. And that clear liquid is representing those acetone molecules. When acetone is in huge populations, like in that clear liquid, the populations themselves take on their own personality. The personalities of populations of a molecule are the physical properties of the molecule. You can look up physical properties in reliable handbooks like the CRC handbook on the left or the Merck index on the right. One physical property has to do with the phase of the molecule. Is it a solid, liquid, or gas? Among other things, that has to do with the temperature that the molecule is at. Acetone will be a solid at temperatures below negative 138.5 degrees Fahrenheit. Between negative 138.5 degrees Fahrenheit and 132.9 degrees Fahrenheit, acetone will be a liquid, and above 132.9 degrees Fahrenheit, acetone will be a gas. Compare that with water. Water turns into a solid at 32 degrees Fahrenheit. So acetone will stay a liquid at lower temperatures, much lower temperatures than water. Water boils at 212 degrees Fahrenheit. So acetone will boil at a much lower temperature than water will. As a scientist, you want to think not just in terms of degrees Fahrenheit, but even more in terms of degrees Celsius. So consider again, acetone would become a solid below negative 94.7 degrees Celsius, a liquid in between negative 94.7 and 56.1 degrees Celsius, and a gas above 56.1 degrees Celsius. Again, compare that with water. Water freezes at 0 degrees Celsius. So you can see acetone staying a liquid at much lower temperatures than that. Water boils at 100 degrees Celsius. So acetone will evaporate at much lower temperatures than water would. You can use these freezing and boiling points to separate mixtures. If acetone is in a mixture, for example, you could cool the mixture down so that acetone freezes at negative 94.7 degrees Celsius, and the other things in the mixture don't. It'll harden out, and then you can strain it out of the liquid. When you separate things based on the freezing point, it's called crystallization. On the other hand, if acetone is in a mixture, you can heat it up to 56.1 degrees Celsius. The acetone will evaporate, and the other molecules may not, and you can collect those vapors on the underside of a container, and then have them drip into a new container. When you separate a molecule based on its boiling point, that's called distillation. Solubility is another important physical property because it creates structure within a fluid. Let's consider the solubility of acetone in water at room temperature. Solubility, or whether molecules mix together, has to do with whether they both have electrical charges or both lack electrical charges. Electrical charges tell you the stickiness of a molecule. Opposite charges attract, so positive charges will want to stick to negative charges. You can see in water on the right here, the oxygen is really electronegative, pulls electrons to itself, and becomes slightly negative. The hydrogens in water lose that electron density and become slightly positive. So every atom in water has a charge, Another way to say that is water is very polar, and it will want to stick to other molecules of water. The slightly positive hydrogens on one water molecule will want to stick to the slightly negative oxygens on another. In order for acetone to be introduced to water and mix with it, the water molecules will have to be as attracted to it as they would be to another water molecule. Because you can see with these red and blue regions of acetone, which are very large and dark, that acetone is also very polar. It has lots of charges. You can see that water will want to mix with acetone. The slightly negative oxygen on acetone will be attracted to the slightly positive charges on the hydrogens of water. And the slightly negative oxygen of water will be attracted to the slightly positive carbons of acetone. And so acetone will mix with water. And in fact, acetone is completely miscible in water at room temperature. That means that it will mix perfectly with it. There is no upper limit to how much it can mix with water at room temperature. A final physical property to think about is density, which is significant because it creates structure based on sinking and floating. More dense objects sink, less dense objects float. And that creates layers, like the layers in the core, mantle, and crust of the Earth, or layers in the atmosphere. As, for example, warm air becomes less dense, it starts to float, and the hole it leaves behind allows cold air to flow through, and differences in density create the wind in that way. The density of acetone is 0.7845 grams per milliliter. Compare that with water, which has a density of 1 gram per milliliter. Because the density of acetone is less, it will float on top of water. Hopefully this video has given you a better sense of the molecule acetone.